starting actually, and he got means collaboration with ONGC actually yesterday
Hmm.
only, and
Okay.
they are going to invest 8 crore in his company actually in that way.
Yeah, yeah, he was telling me about that.
Um, s- so we can start, then we can talk this later. So,
Okay.
very good afternoon to everyone present here. So, this is the third sessions of today, actually the second day of our ongoing STC on computational methods and analysis for engineers. So, the speaker of this talk is Dr. Srinivasa Babji. So, let me introduce you all. So we have amidst us Dr. B. Srinivasa Babji, who is currently working as freelance consultant. Prior to freelancing, he was associated with GSFC Limited, CMC Limited, Garda Chemicals Limited, Yokogawa India Limited, ABB Limited. He has over 30 years of industrial experience in the area of R&D, engineering, sales and marketing, and services related to advanced automation solutions and services. Dr. Babji has a luminous academic record, having completed his BTech in chemical engineering from Andhra University, Vizag. He completed both his MTech and PhD in chemical engineering from IIT Kanpur. He worked in the area of computer process control for the PhD. He has 10 conference presentation, publications, and 4 international patents. So, with these short introductions, I would like Dr. Srinivas Babji to conduct the sessions. Over to you, sir.
Okay. Thank you, Dr. Rajkumar Arya, for the kind introduction. Okay. So you are able to see the
Yes,
slides?
sir. Yes, sir. It's visible now.
Okay. Okay. Good afternoon to all of you. I'll be explaining about data analytics, their applications in process industries. Outline is I'll give you a brief introduction to what is this data analytics, how it is relevant in the context of process industries. Then I will explain that through control loop performance monitoring, this is one some sort of a case study or use case you can say. Then we also talk about soft sensors applications. Then we can have questions and answers. Like in our day-to-day life, we deal with so many things like whatever we use as a what we call consumer products, energy, all activities of lives are linked in some way or other to various process industries. For example, if you talk about our petrol, diesel, which we use in our cars, goes to it is produced in the petrol refineries. Then paper that we use for our writing and reading, that is coming from the pulp and paper mills. Cement plants, they provide all the material for our constructions. Iron and steel, same, like they provide all the raw materials for various construction activity. Then power plant, thermal power plants, they provide the energy for us. So all these process industries, they use control systems. When I say control system, there are different types of systems are there, like DCS, that is a distributed control system. Then PLCs, programmable logic controllers. So these are all basically computer-based control systems for automatic operation of all these plants. These automation systems are designed in such a way that these plants, they run without any issues, without any breakdowns or operational problems 24 bar by 7, 365 days. They're basically like non-stop. except for maybe typically in a year they take for shutdown for maintenance and all, maybe for a couple of weeks. Other than that, the remaining days they will be operating in continuous manner. So you can just imagine how to make sure that these plants, these process industries, process plants, they are operated continuously without any hitches. And that is done primarily through this computer process control system like DCs and PLCs. What these control systems they do is they gather this data from hundreds and thousands of sensors. Like you take a refinery, there will be some maybe easily about few thousands of signals will be there. So this, when I say signal, they are basically sensors and transmitters which provide the information about the process variables like temperature, pressure, and things like that. So all these signals or the process variables information is gathered by these control systems, like typically every 1 second, and use that information in some specific control logics and algorithms for safe operation of all these plants. So you can imagine, like when you are getting these thousands of data points at every second, how much of data you will be having actually. If you consider a year or two, actually there will be thousands or millions and millions of data points will be available. Okay, but what currently happening is most of this data that is being collected, let's say typically at every second, only about 20 to 30% of data is primarily used in the operation of the plant, typically either in the form of control logics or maybe in the form of some process information for management purposes. So that means almost like 80% of the data is really not utilized properly in the industries. So efficient utilization of this data, like since we are having a lot of buzz around this artificial intelligence, machine learning, Internet of Things, since these things are really becoming more what you call ubiquitous now, everywhere people are talking about and how to use them in various domains. So if you use this type of technologies for analyzing this data and use that information for some actionable implement of activities, that will easily result about 30 to 40% improvement in the process industry. So you can imagine, like all this huge amount of data that is sitting in these process control systems, if we make use of them properly, it will straight away improve the plant performance by 30 to 40%. Okay. This is a typical automation system where we have all these sensors that are located in the field. It means providing all these process measurements. They basically are connected to this microprocessor-based control systems, and where actually this control logic is executed. And on top of it, basically you have these computers which are used to as operating stations or either for engineering applications or for management information systems, reporting and things like that. So this is how a typical automation system looks like. Like if you use this, all the data that is being collected continuously from all these field instruments, and utilize the data for various purposes like predictive maintenance, process analytics, operation management, supply chain optimization. There are so many things that can be done with this data that is being collected in the process industries. Okay. So this is a typical some sort of architecture that represents this data analytics system. Like you have all these field signals that is being available in this process control system. Typically, we use one hardware. When I say hardware, it is typically one high-end computer system. So this computer system, okay, as per this current terminology, we call it as an edge device because it is sitting close to the control system in the process plant. And it has all the applications, programs, software applications, which are running in this platform, computer platform, which we call as an edge gateway and things like that. And all this analysis of the data, it takes place here. So we call it as an edge analytics. So All the data collection analysis takes place in the plant, and the results are available for use by the plant operation scheme, typically in the plant environment only, in that particular plant. Okay. This we call as on-site or on-premise data analytics system or edge analytical system. Okay. But if you have some companies, some organizations, industrial organizations have plants in multiple locations. If you have one single plant in one single location, maybe this will be good enough. Suppose if you have multiple plants in multiple locations, for example, like our Indian Oil Corporation, if you talk about, it has refineries in Mathura, Panipat, then Baroda, Haldia, Barauni. So many places it is having refineries. So if you want to, you have some sort of a data analytical system. So one should go for implementing this edge analytics in each and every plant in each location, which is again expensive. So instead of having that insight, what we can do is you can host this in some sort of in the internet on a web based system, like a cloud based system, very much similar to our Google Meet. Like this Google server is sitting somewhere we don't know, but all of us are able to log in and what we call carry out with whatever work we wanted to do. Something similar to that. When you have this data analytics software implemented on some computer which is located in the cloud, then the people in the plant also can access that through internet, and also various management teams, plant management teams sitting in different locations, they also can log into this cloud based data analytics system and make use of the analysis. So this is how typically it operates. So once the system is implemented in this cloud-based server, so the data is collected by these edge analytical tools, and they basically pass on this information to the cloud-based system, where you have all these data analytic applications running in this cloud-based server, and all the results are available. And all the key stakeholders like general managers or plant managers, all those people can view this information that is available in the cloud and take what we call informed decisions about the operation of the plant. Typically, the data analytics are used in applications like, for example, control loop performance management, which I'm going to talk about now. Then predictive maintenance. Many times what happens is, till recently, people used to follow the maintenance practices based on some fixed schedule. Okay, every year on so and so month, you stop the plant and carry out all the maintenance activities. Then that is really not a very efficient way of doing it. So what nowadays people are doing is, they basically, since the data is available from the plants continuously, they make use of that information and they're able to predict which equipment requires maintenance. Instead of doing in a time-based, schedule-based thing on a reactive basis, you can basically go for a predictive maintenance based on the condition monitoring and take corrective actions. Process analytics, so much of data that is being collected about the process variables. You can make use of that information to find out how the plant is performing with respect to design, how it can be optimized further. So all the hidden information from this data can be brought out through this data analytics system for improved performance of the plant. So this is how typically a data analytics system works. So now I will explain you about this control loop performance monitoring diagnosis, because this is one what I call use case you can say about data analytics, because the whole monitoring and diagnosis takes place on the huge amount of data that is being collected from the control loops. So I know that actually when I looked at the topics of this short-term course, perhaps I think most of them are talking about modeling, optimization, solving of equations and all that. When it comes to data analytics, okay, we may not be dealing with what I call solving of DAEs or ODEs or PDEs, but we use huge amount of data crunching, like out of all the huge amount of data that is being made available in the control systems, how to make use of that data through various computations and come up with some useful actionable information about the plant activities So one such thing is the control loop. Like typically a control loop consists of, this is an example where we have a heat exchanger where steam is being used to heat the process stream. Now you have this temperature measurement of the hot water that is coming out of the heat exchanger. Then we have this temperature measurement, which is made available to this temperature indicating and control, where you feed a set point to this temperature indicating control. And based on the measurement and the target value set point, whatever is the error, based on the error, the controller algorithm, like typically the PID controller, it will calculate the output, and the output signal goes to the field, which manipulate this control valve, either increase or decrease the steam based on the current process value. So this is a typical control loop. And in most of the industries, almost like 95% of the loops are using this PID control algorithm, because it is very simple and robust. Like there is nothing much to go wrong with using it, and it is very simple to implement and tune also. So most of the, like 95% of the loops are using this strategy. When I say proportional, integral, and derivative, we are talking about three contributions in this control algorithm. Proportional, the corrective action is based on the error. Integral is based on the cumulative error that is present in the system, in the control loop. And derivative is based on the slope or the rate of change of the process value, measure value, or error. Based on the ray slope, you will take the corrective action. Okay. And if you refer to your control textbooks, what you would have studied in your third year or fourth year, this is a familiar equation that is used for this PID control, where you have these three terms. KC is the controller gain, Ti is the integral time constant, PD is the derivative time constant. Okay, so this is a simple PID control loop. Now, as I mentioned, like almost 95% of the control loops in the plant, they are using this PID controller strategy. So it is very an important asset in the plant. And as I mentioned in the previous slide, it basically includes both hardware and software. The hardware is the sensor and transmitter, which is installed in the field, the control valve and the actuators. So they are the hardware, and the software is basically the PID control algorithm that is implemented in the DCS or the PLC, in the computer control system. Okay. Now the PID controls are primarily designed to regulate the process. When I say regulate, its job is basically to keep the process variables at the desired set points. There could be some disturbances because of some changes, load changes. If there may be changes in the feed flow rate, or there may be changes in the feed quality. Even though such disturbances are taking place, the job of the PID controller is to keep the process value close to the set point. So by doing so, its job is it will reduce the quality variations in the process variable and also improve the operation, because the whole control logic works along with all other automation logic, so that the whole plant is operated in an automatic way, improving the operations. Okay, so that way PID control, it plays a very important role in the operation of the plant. But what has been observed is they are not maintained well, and sometimes actually because of the poor performance of PID controllers, it is sometimes even affects the production and the quality of the product that is produced. Okay, several industrial studies have been carried out, and what they found is about this particular, you can see this pie chart. They found that only about 25% of the loops are working properly. That means they are able to regulate the process properly. Okay, the remaining 25% of the loops are having issues like manual operation. Many times it happens when you go to the plant, collect the data, and do the analysis, you find that almost 30-35 percentage of the loops are they're operating in manual operation. Then about 15 to 20% of the loops, you'll find them as output out of range. That means they are in saturated conditions. That means the output is either at maximum limit or the minimum limit. The remaining 30% of the loops, even though they are on automatic and working, they are having a lot of variations. These variations are maybe because of the tuning, or maybe because of other process disturbances or some other reasons. Okay, so that way you can see that if only 25% of the loops are really working properly and the remaining 75% loops are not working, that means something is really not well with the current state of the PID control loops. So if you improve this performance, instead of only 25% loops working, if you make around 80 to 90% of the loops working properly, then it will give you a lot of benefit in terms of improved plant performance. It also has been reported that like to make sure that all the PID controller are working properly in the plant, straight away it will give you 1 to 2% savings in the operating cost. That means without implementing any new equipment or anything, by simply making sure that water PID loops that are configured already in the control system, if you make sure that they are tuned and working well, you will get an improvement of 1 to 2%. Okay. So if that is the case, then what is the why the PID controls performance deteriorates? Because when you do the engineering and commission the plant, everything has been done as per the requirement. Whatever has been decided in the design, it has been implemented. Okay, then what is the problem? Many times what happens is the process characteristics, they change over a period of time. Initially, okay, you would have designed the plant, but after some time, what happens because of some market requirements or there may be some other requirements, you make some changes in the plant design itself. You do some debottlenecking, you modify the process, add some new equipments. Like this, you make some changes in the process. Because of this, again, the process behavior changes. The performance of PID controllers is directly linked with the process behavior. Okay, so if there is a change in the process behavior, the PID controller also has to be adjusted or tuned. If you do not do that, then the performance will not be good. And other reason is many times this equipment falling takes place gradually. All the heat exchangers initially they'll be good, but gradually they'll be falling. Then you may be doing the cleaning. So during this process of falling, which is taking place continuously, the performance also deteriorates. Then plant loads also will change because based on the market requirements, you will either increase the production or decrease the production. So that again will have a bearing on the um, performance of the behavior of the process plant, because we know that most of the chemical processes are non-linear in nature. So if you are operating at different loads, the behavior also will be different. Then seasonal changes, summer and winter, again, particularly in North India, you have drastic difference between summer and winter in the environment temperatures. So that also will have an impact on the heat exchange performance and things like that. So all these factors, they result in change in the process behavior, which in turn will affect the performance of the PID controllers. And operation, sometimes operators also keep some of the loops in manual and operate the plant because there are some issues, like maybe some design issue or some other issue, tuning issue, because of which they are not able to operate these loops in automatic mode. So since operators did not have so much of time available to them to do some detailed investigation to that, what they do is they just put it in manual and operate it manually. So that also will lead to deterioration in the PID control loops performance, okay, because it has to be done managed by the operators manually. And next one is this control valves. Many times we have this hysteresis problem, stiction problem, valve sizing problem. All these problems again will lead to poor performance of the PID controller. Then the last one is the tuning parameters. Typically what happens is when you commission the plant in initial stages, you do the tuning of all the control loops and make sure that plant is working properly. But over a period of time, like you can see that because of all these changes in the process behavior and all that, then you need to do retuning of the PID controllers. If you do not do that, because of this tuning parameters being not appropriate, that again will lead to poor performance of PID controllers. So these are all the reasons, these are all the factors that contribute to the deterioration in the plant performance, the PID controller's performance. So what is that? The industry is primarily looking for, it is basically the needs are, so we have hundreds of thousands of loops. So they need some system which will be able to collect the data from all these control loops without much problem, without disturbing the plant operations. Okay. Then the performance of the control loop should be quantified. Like you should be able to tell, okay, 20%, 30%, 40%. Simply saying good or bad is not sufficient for the plant engineer. So you need to quantify the performance of the control loops. Then this control loops performance monitoring and diagnosis, whatever is mm, planned to be done, it should be advisory in nature. Like you should not do any closed loop automatic corrections. It should be only advisory in nature. And also you should not make any changes in the non-invasive. It should not disturb the or not make any changes in the process operations. And also they do not want to invest in any new additional equipments or instruments for the sake of control loop performance monitoring. Whatever is already installed and available, only those equipment and measurements needs to be used in this monitoring and diagnosis. And also what are computations algorithms that are being used for monitoring and diagnosis, they should be simple, and the loop performance monitoring application should be able to diagnose, collect the data and analyze and diagnose the loop, many loops at a time. It's not that one by one you will be analyzing loops. Suppose if I'm having, let's say, 1,000 control loops, the system should be able to collect the data from all the control loops, 1,000 control loops, analyze and primarily tell that, okay, all these 1,000 control loops performance is like so and so at a particular time, like that. So this is basically what industry is looking at, and that is what has been developed by several. A lot of R&D work has gone into this control loops performance monitoring diagnosis in the past 20 years. And based on that outcome, now we are able to have this software tools available in the market based on the solid R&D work that has been done in the past 10, 20 years. The tools are available now, and we are able to monitor the performance of the control loops and diagnose issues successfully in the plants now. Okay. So what type of data is typically collected for this control loop performance analysis? The data is collected from all the control systems at typically at around 5 seconds interval, and the analysis is performed typically once in a shift or once in a day as required by the customer. So typically what happens is you keep collecting data at 5 seconds interval. At the end of the shift, whatever data that has been collected, 8 hours data, that will be analyzed, and then the results will be provided to the users about the performance and diagnosis of the loops for that particular shift. Like that, it goes on continuously. Okay, so this is the basically the data that is used, process data. We typically call it as a time series data. Here, when I say time series data, it is basically the dynamic process data. That means at each sampling interval, you have this process data as a one set or one record, and like that you have this data at each different sample. If I am collecting for every 5 seconds, so at every 5 seconds you will have one record containing the process value, set point, and control output for each of these PID controllers. Okay, so this is the dynamic time series data. That is the dynamic data that is collected. Then we also use static information, like typically high and low limits of this process value, control output, and the set point. They also are required for doing this analysis and diagnosis. So we collect this information also. Typically, it is available in the engineering application, engineering software application that is used in the process plants. Then we have this additional information like loop type, typically whether it is a flow loop, pressure loop, temperature loop. We need that information. Then criticality, if you are having thousands of control loops, obviously like they will have some loops which are high priority and some loops are which are low priority. If you have such prioritization of the control loops based on their importance, that also will be useful information. Then we also need to have some basic process know-how, because when I say data analytics and when I'm collecting data and doing the analysis, it is more like black box type of analysis, in the sense it will not really look at anything related to the process design in terms of what type of reaction kinetics are there, whatever is a first order reaction kinetic, or what type of catalyst is used. So it will not look into any of those things. It will simply look at this input and output data, and based on this various computational techniques and algorithms, it will analyze the data and give the results. So if you have the basic process know-how, like how the process flow is there, that will be helpful to you when you are interpreting the results from this uh, performance analysis. Okay. So this is about the data that is required, that is typically collected for doing this performance analysis. So typically what we do is, once we collect this data from all the process signals, as I mentioned, a batch process data means if I collect data at 5 seconds and at the end of the shift, I have a batch data for about 8 hours. Okay. So I use this 8 hours process data and calculate lot of, I do here a lot of computations, and we have different type of indices which reflects the, it tells us about the how a certain part of the control loop is behaving. So these indices are calculated, and from these indices, the diagnosis is made based on this rules or hypothesis. We have a lot of diagnosis rules are there. So based on this index values and the rules, then I will come out with the results of the diagnosis. Okay. So this is what happens typically in this control loop performance monitoring application software. So you have this data, time series data, then static information collected, then we have this all the computations, all the computational algorithms are here where they make use of this data and do the calculations. Then the outcome of these calculations and the diagnosis rules, based on the rules and the values of these calculations, we come up with the diagnosis rules. Typically, the results are expressed quantitatively between 0 to 100. That means if the value is 0 means it is no issue, there is no problem. If the value is 100, there is an issue problem in there. Okay. So this is how typically the data is collected and analyzed. So now I will tell you about the various computations that are carried out for this performance monitoring of this control loops. First is we do this basic statistics calculation. That means mean value, averaging the value, standard deviation, variance are calculated for all the process variables, control output, and the error signals. Then we have another calculation that is related to automatic status. What it does is, if you look at the values of the control output, if they are remaining constant for a certain amount of time, then it assumes that it is not changing. So like that, it will, the whole data, in the data set, it will see how many times it has remained constant where it is not changing. That it will calculate the percent of time, and it says that during this time, the controller is not in automatic mode, but it is in the manual mode. Okay. Then percentage of saturation time. This again indicates like the percent of time in the data that has been collected, percent of time where the control output signal is staying at the high and low values. This problem we face in several loops. Typically, when you go to the plant and collect the data and do the analysis, you will find many times this control loops output remaining at the high limit or low limit. Okay. Then we have this wall travel. This index, it calculates how much time the control signal moves during this batch, data batch. This gives actually about the vigorousness in the control action, because it is really not a desirable state, because if there is too much of travel, it gives actually leads to a lot of wear and tear on the control valve actuator. Okay. Next one is oscillation index and oscillation amplitude. Actually, what oscillations means, basically they are having more variation in the process variables. It is, which is not again desired what we call status. So we calculate the oscillation amplitude and the frequency, at what frequency these oscillations are taking place, and what is the amplitude of these oscillations. And also we calculate an index based on this. Okay. And another calculation that is carried out is the power spectrum. Okay, in the chemical engineering, we may not be, we really do not use this fast Fourier transforms, but when we talk to our colleagues in electrical and telecommunication department colleagues, they use this fast Fourier transform for all the signal analysis. Okay, So what we do is we apply this fast Fourier transform on the process data that is collected, and it will tell us about the and use it to calculate the power spectrum. So if there are no large variations, if there are no major oscillations or disturbance in the process, the power spectrum will be more like a steady with a very small what we call variations, which is remaining constant throughout. Suppose if there are a lot of disturbances or large variations, they appear as a spike at that particular frequency in the power spectrum. So this way, it is very easy for us to identify at what frequency these oscillations are taking place, and also then at that particular uh, frequency, what is the corresponding amplitude also we'll get it from this Fourier transform. Okay. Then next we calculate this noise index, because many times when you are dealing with the process signals in the industry, you will come across this noise issue. Okay. So here what we do is we collect this noise index, which tells us about how much of variation in the process signal is contributed by this noise. And typically it should not be very high. If it is very high, then we need to filter that noise by applying some filters on the process signals. Okay. So we calculate the noise index also. Then another thing which we calculate is the set point crossing. How many times the process variable is crossing the set point. Typically, if the control is proper, then you will see that the process variable will be very close to the set point, making some crossings occasionally. Okay. If there are very few crossings of the process variable on the set point, then it indicates that there is a sluggish control. Okay. So indicating that it is basically having some an offset issue also. So that is how we make use of the set point crossing calculations. Then another calculation that is done is shut off of the emission. When the control output is 0, what is the value of the process variable? Suppose, ideally speaking, if the control valve is not leaking, when you close the control valve and the output signal is 0, there should not be any flow signal. But if you find that at shut off PVR, when the control output 0, if there is a process variable variations, like flow is varying and all that, it indicates that the valve is leaking. Okay. Then another index called Harris index is calculated. This index gives information about the overall control performance. What it does is it compares the standard deviation of the control error to the minimum variance control. This minimum variance control is what is the minimum variations in the process variable. When the control is perfect, the only variation that is present in the process variable is basically coming from this noise, white noise that is present in the process signals. Okay. So what we do here is we calculate from the process data, we calculate this standard deviation, the process signal, and also the variation or the standard deviation that is coming from the minimum variance controller. Okay. For calculating this, we need to have an idea about the delay time that is present in the control loop. So if you know about the delay time, then it is possible from the data that is available to calculate this standard deviation from the minimum variance control. Here again, for calculating this minimum variance controller standard deviation, we again actually fit the time series model to the process data, then estimate this variance from that. Okay. Then another calculation that is done is autocorrelation function. This basically tells us about whether the particular data that is at time t, how it is correlated with the past data of the process. So it gives us an information about the autocorrelation, the relationship among the process variable at different times. So this is a formula used to calculate this. Here we calculate this y is the process data at ith sampling interval, and y bar is basically the average value, the set point. And we make use of this formula to calculate this autocorrelation function values. Then another one is this PV and CO diagram. That means process variable and control output diagram. The shape of this diagram, typically if the diagram is having some sort of parallelogram or ellipse shape, when we plot this control output in the process variable, it gives an indication of the presence of the stickiness in the control wall, hysteresis. Okay. So like this, we do various computations. You can see that we are doing a lot of data crunching based on this process data that is collected from the control systems and carry out all these computations in the data analytics system. Okay. There are few more, actually, a lot of other indices are also there. I'm not covering all of them. Okay. So once you calculate this indices, okay, then we have various hypotheses here actually. Like, for example, we have a hypothesis saying sluggish tuning, oscillating loop, possible wall problems are there, then wall leakage is there, oscillating set point is there, excess wall movement, noise, excess noise. Like this, we have different type of assumptions or hypotheses. Okay. Now, based on the indices or computation that were calculated, we have certain limits for each of those diagrams calculation that we do for various indices. Okay. Now, based on the limits, if it's more than that limit, then we say that that particular indices value is more than the limit. So that is used in this evaluation of this hypothesis. Okay. When we evaluate this hypothesis, you can come up with the results like it can be either true. That means if the sluggish tuning based on what I say, autocorrelation coefficients, if I find that the loop is having sluggish response, if that is, if the value, the index value is more than the limit, then we say that, or it is true that it is having sluggish tuning. Or if it is not there, then we say that it is false. It is not having that particular issue. Sometimes because we are dealing with real life data, we may not be able to conclude anything correctly, either false or true. So we leave in those cases undecided also. Okay. So like this, when we evaluate, we'll come up with this results for each of these assumptions or hypotheses. For example, if you want to say that the loop is acceptable, like it is overall performance is okay, that is possible only if this Harris index is good, the set point crossing are large enough, then loop is not oscillating, loop is not saturated, loop is not in manual mode, the control valve have no leakage, there is no sluggish tuning. So by evaluating all these hypotheses based on the numerical value that we obtained from this indices that I've calculated, then we'll come to the conclusion. Okay. So this is how actually the diagnosis is usually carried out. Okay. This is one example where we are having this oscillating loop. We have this in this plot. We have this red color is the set point and the blue color is the process variable. In the bottom trend is the control output signal. Okay. Now for this data, I calculate all the indices and calculate the values of this results of the hypothesis. This is what we got. Sluggish tuning 0. That means it is false. Loop is oscillating is true. Wall problem is false. Wall leakage not sure. Set point is oscillating false. Wall travel is not sure. Noise is false. Like this. So finally we say that loop is oscillating. Okay. Since loop is oscillating and it is not because of this tuning or the wall problem, then we conclude that it could be because of this some external disturbance. Okay. So this is basically the outcome of this diagnosis. The result of the diagnosis, loop is oscillating, and probable reason is because of some external disturbance. Okay. Next we have loop which is basically normally operating. It doesn't have any issues. If you, this is how you can see here, it is controlling well, and there is a control output signal also. There are no major what you call any undesirable trends or anything. If you look at this calculations of this results of this hypothesis, all of them is false, and only noise is there. Okay, noise is again, if it is not very high, we can ignore that. Then we say that it is acceptable performance, one it is showing. So we can conclude that for this set of data, the control loop is performing properly. Okay. Next is the saturation example. You can see here the set point is constant and the process value is also varying, but the output is constant at zero value. Okay. Now, when we look at this hypothesis values, you can see here only this saturation, control saturation is true, whereas all other values are hypothesis results are negative. So we conclude that it is having a control output saturation problem. So this is how actually we do this identification of the performance issues in the control loop. Okay. So these are various examples of hollow flow control and output saturation, valve friction. When we are having valve friction problem, there is a particular type of behavior in the process signals. Okay, and this is oscillatory disturbances. Control valve sizing, you can see here most of the time the control valve output is close to 100. So when it is close to 100, if there is some disturbance, then it will not be able to act on the control error, then because of the limitation of the control valve size. Okay, which leads to what we call undesirable control performance. Now, okay, we have developed the control performance monitoring and diagnosis information, and we deploy it in the plant so that I get a continuous information feedback about the performance of the control loops, what type of problems it is having. Okay, now once this is information is available, let's say every shift in the plant, it is very easy for the plant maintenance engineers to look at those results and focus on implementing the corrective actions on those high priority loops having these problems. Okay, once you implement the corrective actions, then you will not be able to find the similar type of issues again for some time. So typically in the plant, what we do is we implement this control loop performance monitoring system, and the operators or the maintenance engineers keep looking at the results. If they find some loops are having specific issues like stiction in the wall, that means they'll go and do the maintenance in the control valve actuator. If there is a tuning problem, like if the loop is responding very sluggishly, then they will go and retune the PID parameter, tuning parameters in the control loop. Like that, they take all the corrective actions so that the performance improves. When we implement such what we call continuous performance monitoring and tuning and improvement system in the plant, you will get improvements in the plant from two reasons. One is the variability reduction. Once you tune the loops and make them work properly, the variation in the process variable will reduce. Once you have less variation in the process variable, that will help you to save raw materials and also increase the production. And the time to target reduction. Once you tune all the loops and make them work quickly, means they will respond to the changes, set point changes quickly. It will help you to reduce the aspect product. It also helps you to increase the production because you are able to reach the set point for any new grade in a shorter time. So it will result in net increase in the production. This is what is shown here in this picture here. Suppose there is so much of variation in the PI control loops performance. Then because I will implement this control loop performance monitoring diagnosis system and implement all the corrective actions based on the diagnosis results, and I'll be able to reduce the variation to a smaller value. Once I have what we call smaller variation, then I'll be able to operate closer to the limit. So I can shift the set point and take it closer to the limit. And this shifting of the set point gives me the actual economic benefit. For example, let us take a simple example of paper plant producing about 1,000 tons per day with a moisture target of 8.5%. This is what is shown here. 8 point, it should not have more than 8.5%. If the control loops performance is not good, what operators will do is, this is the green color is the histogram. So they will operate the set point far away from the limit because there is so much of variation in the signals. Okay. Now, if I implement this performance monitoring, diagnosis, and tuning system in the plant, I'll be able to reduce the variation by improved performance of the PID controllers. Once I have a improved performance, I'll have less variation. So this blue color is basically the histogram that is basically coming from the improved performance. Since it is having less variation, I'll be able to shift the set point closer to the target. That's what initially they are operating at about 7.3%. Now, because it's improved controller performance, I'll be able to shift it to 7.7%. So I'm able to change the set point by about 0.5%, which results in the energy savings. If I'm producing 1,000 tons per day, it's almost like 4 tons per day of water. Removing this water from the paper, whatever is the energy that is being used, I can save that much of energy. So you have straight away, it will give you energy savings. And also this 4 tons per day of water that you can pass it along the paper. So that means you can even sell that this amount of water as a paper also, because up to 8.5% of moisture is allowed in the paper. Okay. So like this, there are several examples how this controls performance monitoring, diagnosis, and tuning improves the plant performance. This is one straightaway example of how data analytics is used in the process plants to improve the performance. Okay. Next, I will explain about the soft sensors. You might have heard about it. Soft sensors are they have been successfully used in the industry for the past 10 to 20 years. It so happened that because before this hype about this AI, ML, machine learning, or the IoT data, digital, people were using this database modeling successfully in the process industry. And soft sensors technology is one such. When I say soft sensor, primarily what we are doing is we make use of the data that is available, all the process measurements that are available, and make use of this data-driven modeling concepts to predict the quality variables. Okay. Many times in the refineries and other process industries, you will not be able to have online measurement of the quality variables. Typically, what they do is they analyze the sample maybe once in a shift or once in 3 hours or 4 hours. And based on the analysis results, the operators will try to tweak the set points or make some changes in the controller settings to meet the requirements of the control quality. Okay. But if you have the soft sensors, what we can do is based on the process measurement which is available at, let's say, every 1 second, I can make use of these measurements, use this database modeling techniques, and predict the quality variable. So once I have implemented this, I'll be able to get this quality information at every second, instead of getting it every 4 hours or every 8 hours from the plant or from the laboratory. So that is the main advantage. And these soft sensors or inferential sensors are complementary to the multivariable process controls in many applications. In many applications, particularly in advanced process control, the focus will be how to improve the quality control, like how to improve the how to reduce the variation in the product quality. For that, if you do not have a measurement, then it becomes really impossible for the control strategy to control it. So since the laboratory information available only once in 4 hours or once in 8 hours, this soft sensor will provide the advanced control strategy, useful information about the quality, like every few seconds. So that's why actually it has been successfully used in conjunction with advanced process controls in many industries. And there are many quality variables that have been where the soft sensor has been used in the process industry. Some of them are basically particularly polymer melt index, then in terephthalic acid, 4-CBI impurity, then kerosene flash point, all our petrol, diesel, lot of properties, quality parameters, octane number, and all this flash point, 4 points, and RVP, vapor pressure, all these properties are, they are able to predict through soft sensors nowadays. Then we also have in the pulp and paper industry also, they are using soft sensors for properties like kappa number, brightness, and all that. Typically here again, since we are talking about data analytics, the central to the theme is basically collecting data. So here also what we have to do is This is a typical environment where we have this plant, then we have this data DCS control system, then we have the laboratory. So from the plant, all the measurements are available at every 1 second in the DCS. Then from the lab, typically they collect the lab samples every shift or every few hours, bring the sample to the lab and analyze, and the results are available in the laboratory information system. So both the plant data as well as the laboratory information system, they basically contain results of this analysis as well also corresponding process data. The whole information available in the process database. Okay. Now, once this data is available, then we do a typical pre-processing, like we remove the outliers, filtering of the data, we smoothen it and make it proper for using in the offline modeling system. Then this data is divided into two sets. One is the training and the validation set, because the training data set is used to develop the model. And once the model is developed, then it is tested or cross-checked using these validation data sets. Then we have to select the model inputs and outputs. There are some techniques which will help the users to decide about the inputs. So once we have this, then we train the model and test it. And once it passes the validation test, where the required accuracy is obtained, then it is ready for online deployment. So this model information we create in the form of a file and keep it ready for the online deployment. So this is all these activities are offline. Okay. Once we complete the offline activity, then we go to the online activity where we set up the data collection from the control system, because here in the earlier case, the process data is collected in a database and stored there. Whereas here, since we have to predict this quality information, quality variables online at every 1 second, so we have to set up a data collection specifically for this, where the required inputs are collected, and you have to define what is the model inputs and outputs, and then based on the offline model that has been developed earlier, that will be deployed in this control system. It is loaded in one of the computer systems here. Once that is done, then based on the actual data, it is able to predict the quality variables continuously. And one thing which we need to take care during this online deployment is bias updation. However good the model may be during the validation stage, once we deploy it online, because of some various process disturbance, you will not be able to have a 100% accurate prediction of the quality variable. So whenever we have this lab data available, so that will be entered in this system and compared with the predicted values. So there could be some difference between the predicted and the actual value available from the lab. So based on this difference, we have to update the bias. That is, the model that is already available, its bias will be updated, so that from that time onwards, again till the next sample comes, the predictions will be good based on the updation. Okay. So once that is done, then you have this continuous online expression of the model, and you will have a user interface to monitor the performance of the sub-sensor. So this is how actually it works in the online mode. Okay. And when I say data pre-processing, typically we again calculate this basic statistics to analyze the data, what is the range and what type of variation it is having. Then we detect all the suspected outliers, we remove them. Then we do a correlation analysis, because for us to decide what are the inputs that we need to use in the model, from the several process measurements that are available, this correlation analysis will help us. We will be able to see which variables are having more effect on the output. So we use this correlation analysis to help us to select the inputs. Then we also have to normalize the data, because you will have different type of process variables, pressure, temperature, the ranges may be different. So to have proper results, we typically normalize the data. Sometimes for better results, we do some input transformation, like logarithmic transformations and all that in specific cases. Then we also do some filtering if the data is noisy. Okay, so these are all typically some of the data pre-processing technique that we use in the first stage of analyzing data. Now I'll give you an example how this database modeling is used for the soft sensors. We have an application here, a debutanizer column, where we are removing the LPG on the top product, and the bottom basically are having this naphtha and further which is being split into uh, pentane and all other products. Okay. Now here my focus is I want to control the amount of butane in the bottom product. Okay, of this debutanizer. Okay, I do not have a sensor here for measuring the amount of impurity butane in the bottom product. So here we are going to develop a soft sensor for that. And typically we use this multilinear regression model. This is one way of doing the model development. Here, based on this correlation analysis, we have identified about 7 process measurements or process variables that can be used in this multilinear regression model. So these 7 ones are basically this X1 to X7. They are basically top temperature, then top pressure, then reflux flow. Then we have this 6K temperature, then bottom temperature. There are 2 measurements here. So all these 7 measurements are used as the input. Okay. And the output is basically the C4 content in the column. These measurements, actual measurements of the C4 content in the column are available from the laboratory. So we make use of that for developing this soft sensor model. So once we have collected this data, we basically do all this pre-processing as explained earlier. Then we calculate this parameters like all these A0, A1, A2, A7, all these parameters by using this ML or multilinear regression. Here, basically the X transpose X inverse, X transpose Y. This is the solution that is used in this MLR model for calculating the coefficient, which you are familiar. And from this, actually, we will be able to get these parameter values. Okay, so this is the application of this multilinear regression for soft sensor model development. Okay, so then we have another approach called principal component regression. Here, typically in the multilinear regression, when we are having large number of variables in the process measurement, we have several measurements are available, and it becomes difficult to reduce the size of the problem. Like you have to really spend a lot of time in analyzing the data matrix and decide which are the useful inputs. Okay, many times you have some collinearity in the input data, like a lot of input variables may be dependent on each other. Such data will not be really good when we are using this linear regression. So what we do is we do this principal component regression. We basically decompose the data into principal components. It will basically reduce the size of the problem. Instead of having so many variables, it will reduce the number of variables into the principal components. These principal components are nothing but a linear combination of the actual variables. Okay, like for example, let us say in that input data set you are having, let's say, 20 variables. Then when I convert into principal component, then instead of 20, maybe I'll have only about 7 or 8 variables. These 7 or 8 variables are called as some principal components. Okay, then we can do the regression on using this principal component instead of the actual variables. Typically, these principal components are found by calculating the eigenvectors and eigenvalues from the data covariance matrix. So the calculation that we need to do is we have to calculate the covariance matrix of the data, and from that we'll be able to get these principal components. Typically, these principal components, we want to select those components which are contributing maximum, make a maximum contribution to the variance in the data. Okay. So the results are available, like the first principal component gives the maximum contribution, second will give the next maximum, like that. What we do is we select that many principal components which give a minimum of 70%, which basically contribute to minimum 70% of the variation in the data. Okay. So once we select those principal components, then we basically, what we do is we create the new data set using this latent variables or the principal components. So with this new data set that is based on the principal components, we do the or linear regression, least square regression we do on that. And then based on that, we'll be able to predict the what we call quality variable. So this is how it will look like. In the case of principal component regression, the same way basically B0, B1, these are all the parameters, and PC1, PC2, PC3, PC4, PC1. These are 5 principal components are used compared to 7 in the MLR model. Okay. So this way, actually, principal component regression is very useful in reducing the size of the problem. And also, whatever principal component that we identify and use it in the regression, they are not basically dependent on inches, they are not collinear. So that will improve the quality of the prediction. Okay. So this is another type of modeling that is used in the soft sensors. Apart from this, there are also other techniques like neural networks and genetic algorithms, which have been used because this neural networks and genetic algorithms will be able to handle nonlinear behavior of the process. But one main disadvantage with this algorithms is they work well with the data that has been used. Suppose if you are having a new data point which is outside the data set that has been used for the development of the model, then the performance of this neural networks and genetic algorithms is not that good. Okay. As long as the data lies within the training set region, then it will work very well. So if you want to make use of this neural networks and this type of other genetic algorithm type of model, you need to consider large amount of data sets, which is sometimes difficult in a practical running plant. Okay. So once we develop these models, the next step is to deploy it online. So online model deployment, when we are doing it, as I mentioned, we set up this real-time data collection from the control system. We do this pre-processing. So this online model, whatever the equations what we got, we will be loading them in one of the computer systems on the control system. So online model will be deployed here. Based on the measurements that are available and the model equation, it will be able to predict the quality. Okay. And many times, actually, the estimated outputs are again subject to checks like, okay, they will check whether they are within the high and low limits and all that. Okay. And whenever we get periodic measurements from the lab, what we do is we make use of these lab measurements to update our models. As I mentioned earlier, that bias update. So this will make sure that the model is up to date. The model calibration is done based on the lab measurements that are available periodically, maybe once in an hour or once in a shift and all that. So whenever that lab measurement is available, we'll compare with the model prediction for that particular time instant, and then compare the error, and we update the bias. That is a simple way of updating a model. Apart from that, even advanced model calibration techniques based on the Kalman filter are also used to improve the model predictions. And it has been observed that usage of this Kalman filter method for model calibration based on the laboratory data updates, it really helps in improving the predictions from this soft sensors. Okay, so that can be used instead of the simple bias update to have a better quality prediction. So this is how actually this online deployment of this soft sensor models takes place. Okay. So I explained you about two cases. One is this control loop performance management, and also the soft sensor model development as the applications of this data analytics. And to summarize, actually, apart from this application like control loop performance management and soft sensors, that data-driven modeling, data analytics can be used for predictive maintenance, also process troubleshooting, process performance troubleshooting. A lot of other applications can be developed, which will help in improving the performance of this process plants. One issue with this data-driven modeling or the data analytics is, since they are purely based on this data and they more work more like a black box, So they will perform well as long as the new data point is lying within the data set that has been used for the modeling. Okay. Suppose if it falls outside, then their performance will not be satisfactory. That is where I feel that these new techniques, this artificial intelligence and machine learning techniques can be used to make this data-driven modeling more robust so that they can operate in all operating regions of the plant. Typically, the main problem with this data analytics techniques is they will work well within some certain regions. But if you want to use it continuously throughout under various plant operating conditions, then it becomes difficult because you need to do quite a huge amount of data modeling exercise considering all possible scenarios. Instead of that, if you use something like AI and machine learning techniques to supplement these methods, it will really help in improving the performance of this data analytic techniques. And as we have seen, like data analytics is a very important research area that can really provide solutions of process plants in improving their productivity. And since there is so much of activity going on in this field, in this big data analytics, AI, machine learning, I feel that some of you can take interest in this area and pursue further work in these areas. And here the one good thing is you need to deal with different types of data. One is this simple process data, time series data, what I'm talking about. In addition to that, people are working on video analytics. Like in nowadays, we are having a lot of cameras that are installed in the process plants. So based on the photograph that it is providing about the status of some of the equipments, you can club that along with this data and provide what we call some sort of a complementary data analysis solution. People are working on some very exciting problems using this time series data along with the video analytics to solve some of the problems. So like there are a lot of what we call interesting applications are people are working, and it is a very interesting and exciting research area to work with in the times to come. Okay. So that completes my presentation, and we can have question and answers now.
Yeah, thank you very much, sir. Actually, we academy in academia, most of the places we don't deal actually such thing because we don't have expertise of in that way actually. So we are very glad to see actually such work and actually this. So one thing is one curiosity from my side. So as you started that you have several of data points, right? Several thousands or maybe millions of
Yeah,
data. So how to scrutinize them actually, that which one need to be considered because that is a
yeah,
big challenge, right?
yeah. Actually, the data pre-processing, as you said, it is not that simple and straightforward. But thing is, depends upon the application. Like as I mentioned, um, in the case of source sensors, the first thing what I do is I basically remove the outliers. So there are special algorithms are there.
Okay.
When suppose if you feed it a batch set of data, it will scan all the data sets and then say that okay, these data points are having outliers, remove them. And it will also visually show with some red mark and all that. So it is possible. It again depends upon the type of application that we are handling to identify those outliers and do other types of pre-processing to clean the data and then use it in actual algorithms. Actually, in
Okay.
India,
Okay.
we have in like Professor Godi in IIT Bombay, there are a
Yeah.
lot of
Yeah. Yeah.
people
Gori
working.
sir.
IIT
Yeah.
Madras is having very strong active research activities in these areas. And the main difference is okay, it is not our traditional chemical engineering. That much is there. It is not a traditional chemical engineering where we deal with heat and mass transfer problems and things like that. But it is a different type of field which is mostly used in this electrical engineering department.
Yeah. Electrical and
And
some actually instrumentation and
yeah,
control
instruments, yeah,
actually. So. So other participant can also unmute their video, and then they can interact with Dr. Babji actually, and they can ask their questions actually if they have.
Yeah. May I ask a question, Dr. Raj?
Yes, sir. Yes, sure, sure, sure.
Yeah, so, Mr. Srinivas, you have very rich industrial exposure. I would like to know what is the current industrial scenario with regards to Kalman filter. Are they using Kalman filter based estimation or still they are using the static soft sensors?
No, they are using because I know, like for example, the soft sensor software from Yokogawa, there the carbon filter is used to update the model, calibrate the model, and it straight away, like when we talk about it, we say that it straight away gives you better quality
Yeah.
predictions. So it is
Yes.
used. A lot of this advanced stuff is right now being used in the industry. Okay. Only thing is, okay, you may not be having that much of interaction with the industry to know what is currently happening, but otherwise, there are quite a few advanced algorithms that are being used in the industry successfully.
Excuse me, sir. I
Okay.
wanted to ask a question.
Yeah, yeah, sure. You can ask.
Please.
Sir, I just want to know that suppose the process behavior has changed and all,
Hmm.
how frequently the retuning of the PID controllers are required?
Typically, like, okay, thumb rule is something like typically the behavior of the means retuning the PID controls needs to be done on an average maybe 6 months to 1 year, because it is process specific. I can't simply say that okay, you do every 6 months for all the process. Some process industries maybe once in a year is okay, whereas some process industries maybe once in 6 months. On average, you can say thumb rule is something like once in 6 months. You can say that maybe you need to do a retuning.
Sir, but the PID controllers mostly work as a feedback control. Suppose
Yeah.
there is, suppose in a reactor, in a packed bed
Mm.
reactor, the catalyst activity has degraded.
Yeah.
So, uh, will that feedback control will not be able to handle that change, that disturbance, sir? Means we have to
Uh,
remodel it
See, like
to
suppose
make the
the
retweaning or something.
that maybe directly you may not be able to get it from the PID controller, but indirectly we'll be able to identify that. For example, that control performance monitoring and diagnostic software, what I mentioned. Suppose the catalyst activity is gradually decreasing. Okay, assuming that all other parameters are
Yes,
constant, but catalyst activity is decreasing. If the activity is decreasing, my guess is okay. You may have to increase the temperature. Let us say reactor temperature control. Maybe you have to increase it to maintain the what you call same type of conversion. The temperature, okay, you may have to, the operator may be increasing gradually. Maybe once in a week, he may increase by 1 degree, or once in a month, he may increase by 2 degrees, like that. Set point, he may be increasing. Now, the if you look at the output of the controller trends, it will be gradually increasing.
yes,
Suppose if your controller is not designed properly to take care of this
yes,
deactivation of the catalyst fully, you may end up with a situation where the control output would have reached maximum. Okay. Suppose the saturated.
saturation.
Suppose if the catalyst has deactivated more than what
Yeah.
you designed because of okay, some poison is there, or what a new batch of catalyst is not good, you may end up with control output saturation. So it may not directly come out in the PID control saying the catalyst are deactivated, but indirectly it will reflect in this. That's why I was in the slide I mentioned that it is good to have some process understanding. Suppose if you go to electrical engineer and tell him, okay,
Okay, sir.
what do you mean by this output saturation? He will say it has saturated. There could be some problem. But a chemical engineer, when he looks at the data, he may say that the possible reason
Yeah.
is catalyst activity activation. It has deactivated a lot during this period. So that could be interpretation of a chemical engineer who has some process understanding. That is how we try to correlate the results of the diagnosis with the process behavior.
Okay, sir.
Okay.
Sir, I have one more
Mm.
question. In many times we are not we don't get access to industry's data, and we means we are not able to do our do some of the research on the data and all. So
Yeah.
in that sense, how we can make it in a simulation world, means suppose I have a process model with me, and
Mm.
how I can make the exact, not exact, more or less equal to the industry data, and I can do some of my algorithmic work with that data.
Mm. Okay, in simulation also it is possible. Okay, you can add some noise and you can add some disturbances, but simulation is a simulation because uh, you can in principle uh, create all those scenarios. But my feeling is that I think things are going to change because what I understand now, government is or most of the academic institutes are going to put more focus on having internships. So they are going to have more interaction with the industries. Okay, once that starts,
Okay.
industry also would like to, because in ABB also we used to have internships where we used to get students and ask them to do some work. Okay.
Okay.
Now, once that becomes something like a standard for all academic institutes and industries, okay, they have to collaborate. All the students have to go to internship, industry. Then it becomes more easy to get some data and use it in your actual studies.
Sir, actually,
Mm.
that initiative is already there. Actually, in some institutions at present, they modified the syllabus. They
Uh,
have the 6 month internship. Most of the internship in earlier time, it was just 6 week only.
okay.
So most of the time, industry people, so 6 week is of no, not of
Yeah, yeah.
much use. So they prefer to offer the 6 months actually. So in some universities, most of the private universities, just like Thapar
Mm.
University, Patiala,
Yeah.
BITS Planning, and many more, they have the 6 month projects. So in
Yeah.
that they get a good exposure to industry actually, and at the same time they will become a deserving candidate for a placement offer also
Yeah.
because they are already trained for that company.
Yeah, I
So
think it
that's
will increase now. Actually, more and more institutes will be, I would say, forced to allow internships for students in the industry. Once that becomes something like a norm, then we have more, what do you call,
Yeah, actually, most of the
exchange.
time, because once we give the 6 month free for internship, so some
Mm.
of the course need to be trimmed.
I
So
think,
being completely in academic, we are always scared. Ke, how can we leave this? How can we leave this, that, and all this? So with the help of industry people, that need to be have a, some consensus.
yeah,
This
yeah.
is what you teach here, and rest of the thing can be taken care at the plant site somewhere.
Yeah, yeah, I think it is with the new education policy also. I think they are going to make a lot of changes. I think these things are going to come gradually, one by one.
Yeah, yeah, that's in practice actually.
Yeah.
So, any other question from participants? And yeah, that's the second thing. If a person wants to apply, let's say you work for ABB for
Mm.
several years actually. If
Mm.
someone wants to apply for internship and all this, so what the way and procedure to approach them?
Actually, usually the summer internships, they say that minimum 3 months or 2 months. That is the minimum